So, we will discuss the mean value theorems, Rowe's theorem, Lagrange's mean value theorem and Cauchy's mean value theorem, generalized mean value theorems. Yesterday we have discussed about the local maxima and local minima, and we have seen a function f defined over a interval all metric space xd. F is a function which is real valued and defined on a metric space C. Then we say f has a local maxima at a point P if there exists a delta such that the value of the function at the point P is greater than the value of any number q which lies in the delta neighborhood of P. If it lies in the delta neighborhood of P, and if the image of any point q is less than or equal to the value of the function at P, then we say function f attains or has a local maximum at P. If there exists, P belongs to X, if there exists a delta such that this inequality holds for all q belonging to this, that a d of p q is less than delta. Similarly, when we say it has a f has a local minima at p belongs to capital X, if there exists a delta such that f of q is greater than or equal to f of p for all q with d of p q is less than delta. So, this is the case of local maxima or local minima, and in intervals in a similar way, when we say a function has a local maxima or at the point A, it means there is a neighborhood x minus delta, x plus delta, such that whenever any point t lies in L, then f of t is less than or equal to f x for all t belonging to this range, if it has a maximum, local maxima, and similarly for the local minima. So, with this we have a result which is useful in establishing the mean value theorems. The result is, let f be defined on a closed and bounded interval a b, and if f has a local maximum at a point x belongs to the open interval a b, and if the derivative f prime x exists at this point, then the derivative must be 0. So, what it says is if the function attains a local maxima at a point x in the interval a b, where the function is totally defined, and also the derivative of the function at the point exists, then derivative must be 0. Okay. The same case is the similar statements. Similarly, if let f we define on the closed interval say a b, and if f has a local minima at a point say x belonging to a b, and if the derivative of the function exists at this point where it has a local minima, then the derivative of the function is 0. So, this is the condition that at the point of local maxima or local minima, if it attains and the derivative exists, then the derivative must be 0. Okay. Let us see the proof of this. The proof is say Suppose the function f, which is defined on the closed and bounded interval a b, has a local maximum at the point x belonging to the open interval a b. Okay. Suppose, let us see. So, what definition of this? By definition of the local maximum, there exists a delta greater than 0, such that the functional f of t will remain less than or equal to f x for all t belonging to the neighborhood of x, that belonging to this, that is, this is the point x, and here we are having the neighborhood x minus delta and x plus delta. So, if the function a attains a local maximum at this point a, then corresponding to this we can identify a delta and a neighborhood such that whenever the t lies here, then the value of the function is also less than equal to x, or t lies here, the value of the function will also be less than equal to f x. Okay. So, if suppose t lies between the left hand interval of x, then the ratio f of t minus f of x over t minus x. Now, since t lies between this left hand interval and function attains the local maximum at the point x. So, f of t will be less than equal to f x. So, this part will be negative and t is less than x. So, again this part is negative. So, total is greater than equal to 0. So, this implies that limit of this as t tends to x of this quantity, that is f of t minus f of x divided by t minus x, which gives the derivative of the function at a point x, is greater than, or it cannot be negative. Therefore, the derivative f prime x is greater than equal to 0. This is the first part. Now, if the t lies between this interval right hand towards the right of x, then the ratio f of t minus f of x over t minus x. When t lies here, the f t is always less than equal to f x, because x is the point, a local maximum point, and t is greater than x. So, this is positive. So, this will be less than equal to 0. Therefore, taking the limit as t tends to x of the same f of t minus f of x divided by t minus x will be less than equal to 0, and that will imply the derivative of this is less than equal to 0. So, 1 and 2 combined will give you that derivative will be 0 at that point. So, if it is a local maxima, the derivative exists, then it has to be 0 there, or if it is a local minima and derivative exists, then it. But if the derivative does not exist, then also the function may attain the the maximum minima also. So, that is what we have the corollaries here. As a corollary we can say, the corollary says that if that is, if let R, let F is a mapping from the I to R, I is an interval, be continuous, on an interval, I, and suppose that F has a local extrema. Extrema, when you use the word extrema, means either local maximum or local minimum. So, one word is used for that, extremum. So, if it has a extremum means either it has a local maxima or local minima. So, if it has a extremum at an interior point, say x belonging to I, then either the derivative of f does not exist or it is equal to 0 if exist. So, this part we have already shown, is it not, that if the function attains the local maxima or local minima and if the derivative exists, then at that point the derivative has to be 0. Okay. Now, what it says this result is that once it has a extrema minimum point, the point of the extrema, the derivative will either will not exist or if it exists it must be 0. So, this part way, for example, for this if we look the function f x which is equal to mod x on the interval say I, which is closed and bounded interval -1 to 1. Okay. Then if we look this graph of the function, the graph of the function will be this here is -1, here is +1. So, 0 is a point which is a local minimum point 0. Therefore, 0 clearly the x equal to 0 is the point of local minimum point. In fact, it is a minimum point. Okay, minimum point, that is minimum point of this. The reason is when you take any point closed in the neighborhood of the 0, if you picked up any point of this, then the value at the point 0 will always be less than equal to value at any point, arbitrary point in this neighborhood. So, 0 becomes the minimum point or local minimum we can say. But the function f x minus f 0 divided by x as x tends to 0, that is nothing but what? Mod x by x when x tends to 0, that does not exist. That we have already discussed, because when x is positive the value will come out to be 1, when x is negative the value will come out to be -1. So, the limit does not exist. So, the derivative is not defined, it does not exist, but the point correspond to a maximum, a minimum point of it. So, this is one of them. Okay. Now, this is the one way we have discussed it. Okay, that if the function attains the local minima, it has to be. So, the criteria critical points we can say. So, as a note, the critical points means if the function f is such, the set of all points, where either derivative does not exist or equal to 0 are known as the critical points. So, obviously, the critical points are only the point where the maximum minimum may occur. So, this is the way of identifying. If function is given, first we will find the derivative. If it exists, put it equal to 0. So, you will get the set of points which are known as the critical point, and then we have to test the local maxima and local minima at this point. It means, if the function the point is not a critical point, then there is no question of discussing the maximum minima. In fact, there will be no maximum minima will be occur at the point other than the critical points. So, that is the important part here. Now, we come to the result that is called the generalized mean value theorem. or also known as Cauchy's mean value theorem. Cauchy's mean value theorem. Cauchy's mean value theorem. What this statement says, if f and g are continuous, real functions, on the closed and bounded interval a b, which are differentiable in the open interval a b, then there is a point x belonging to the open interval a b at which f b minus f a over g b minus g a is equal to the derivative of the function f prime x over g prime x, f prime x over g prime f. Of course, here we are we will take up two cases when g b is different from g a and g b is not equal to g a, that we will take. So, g b is not equal to g a, and they are continuous function, and it is where the g b is different from g a. Okay. Derivative will be this. Because that we will say it is not required, but we will just put it. Why it is not required, that we will come to when we go for the Roche theorem. In fact, the Roche theorem says that if the g b equal to g a and g is a continuous and differentiable, then there must be some point where the derivative will vanish. So, derivative vanishes means this denominator will be 0. So, it is not defined at all. So, obviously, this is true, we can say. In fact, this will compute. Okay. Now, here one thing which we can judge, we do not require the differentiability of the function f or g at the end point a and b, because we do not need, we need only the derivative of the function in the interval a b, okay, in the point interior to a b. Now, let us see the proof of this. Let us consider a function h t as f of b minus f of a multiplied by g t minus g of b minus g of a into f of t. Okay. Consider this function. Now, to prove our results, what we want, that there exists a point in order to prove the result 1, we require to show that there exists that the derivative of the function h dash x 0 for some x belonging to the open interval. This we needed. Okay. So, case 1, let us say if our function h is a constant function. Once it is a constant function, then obviously the derivative of this function will be 0 for every x belonging to the open interval a b. Hence, the result follows. Okay, nothing to prove. Now, case 2, if h is not constant, if h is or st is not constant. Okay. Let us take the two cases. suppose h of t, suppose h of t is greater than h of a for some t belonging to the open interval a b. This is our closed interval and t is somewhere here. So, the image of the t at this point is, say here, this is our h a and here is somewhere, say suppose h t is there. Okay. And let x be a point on the closed interval a b at which h attains its maximum, value. Okay. It attains maximum. Now, why it is so? The reason is because this will exist, because h is giving to be this function h we have defined like this, f t minus f a g t minus g b minus into f t. F and g both are giving to be continuous over the closed interval. So, h will also be continuous over the closed interval a b. H, g and f is differentiable over the open interval. So, h will also be differentiable over the open interval a b, and since h is continuous over the closed interval a b and closed and bounded interval. So, it will attain its maximum value and minimum value at least at some point in the interval a b. That result we have seen. Every continuous function on a closed and bounded set will attain the maximum or minimum and minimum value at some point. So, because h is continuous on a closed and bounded interval, say a b, so it will attain at some points attain its maximum and minimum value over the interval a b, that is okay. And so, we can get it x belongs to this. Now, we have seen here is a b, the point x over a b, this is first. Since we have taken h of t is greater than h of a. So, obviously the point x will not be a point, it will be in the interval a, and in a similar way we can say it is lying between a b. So, x lies between this. Okay. Now, further the function h is differentiable inside the interval a b, differentiable at each point in the interval a b, at each point in the interval a b. So, in particular the derivative h prime x exists. Now, use the previous theorem. The previous theorem says this result we have proved that if the function, if f is defined over a closed interval a b and f has a local maximum at some point and the derivative exists, then the derivative must be 0. So, according to the previous theorem, so by the previous theorem, the derivative of the function at this point must be 0, and this will implies that f of b minus f of a is into g prime x is equal to g of b minus g of a into f prime x horse. Similarly, if we assume if h t is less than h of a for some t belonging to the interval a b, then the same argument by the same argument, then by the same arguments applies to the function h, which attains its minimum value at the point x. Hence, we get this implies we get the derivative h dash x will be 0 in a similar. So, derivative of this 0, and this proves the result. Okay. So, this is very now this theorem, which we call it as generalized mean value theorem, in fact it is as a particular case we can derive the our result for this function for Lagrange mean value theorem and Rolle's theorem. So, next result is we get Lagrange's mean value theorem. What this theorem says is, if f is a real continuous function on the closed interval a b, which is differentiable in the open interval a b, then there is a point x belonging to the open interval a b, at which the f of b minus f of a equal to b minus a into the derivative of the function f prime x. The proof follows from the previous theorem. Take g x is equal to x, and the result follows. So, the result follows immediately. Then come to the next, what is the meaning of this? Let us the geometrical meaning of the Lagrange mean value theorem. What does it shows? That suppose we have this function f x over the interval say a b, say here is a, here is suppose I say b. Okay. Now, let us take another graph, because that is very is a and b. It's okay. Let us take this graph, then it's more clear. Okay. Suppose I take suppose I take this graph. Okay. Here is say a and this is say b. Okay. So, this point is correspond to say like this. Now, if I draw the chord joining these points, this is the chord, the slope of this chord a b is nothing but what? F of b minus f of a over b minus a. This is the slope of this chord. So, what this result says is that if a function f, which is continuous function over the closed interval a b and differentiable in the open interval a b, then there will exist a point x in the interval AB such that the slope of the segment joining the end point of this curve will be parallel to this line on the curve. That is, this slope of this and slope of this same. This is the slope is equal to f dash x. This is the slope of this, and here this is the slope. So, both will coincide. So, what this Lagrange's mean value theorem is gives that result regarding the slope. Now, this is the case when both f a and f b are equal. So, we can choose the lowest theorem later on.